name is Maarten.
And welcome to another video in our series of computational geometry concepts, where we take a geometric concept and dive into its definition and history and complexity and other interesting properties.
So the concept for today is the Voronoi diagram.
Man, it's hot. I could really use a snowball. A snowball is the New Orleans version of shaved ice and a useful remedy against overheating.
Of course, there are other ways to prevent overheating. Just go to the beach.
Since their invention in the 1930s, snowballs quickly became popular in New Orleans. And now they're sold at a few dozen locations all over the city. So when the heat comes on and you find yourself at risk, you never need to travel very far. There's a geometric question lurking here. Suppose we're given the locations of all snowball stands in the city. How do we know which one is the closest?
Of course, this question is very easy to answer. We just put all of our locations of snowballs on the map. And we can put them in a big list and then just measure the distance to my location and write all those distances in a list. And then we just look at the list and find the minimum. And that way we found the closest snowball vendor to our current location. And it only took linear time. So that's an algorithm which scales linearly with the number of locations. If I have twice as many locations, it only takes twice as long. That's the best we can possibly hope for, right? Well, the thing here is that my location is actually not stationary. It changes all the time. And as I'm moving around, I never know in advance when I will want another snowball. But the locations of these snowball vendors are actually stationary. So maybe there is something else we can do. Can we somehow store some information about those snowball locations, which makes it easier for me to find the closest one?
So now, given a set of locations of snowball vendors, meaning sites in the Euclidean plane, we can now define the Voronoi diagram for them. The definition is a bit complicated, but the idea behind it is simple. So for each site, such as this one, A, we're going to define a function, fa, from the Euclidean plane to the real numbers, that gives us, for any point P in the plane, the distance from P to the site A. And we're defining such functions for each site. So for B, we have FB, for C, we have FC, and so on. Now for each site, such as site A over here, we define its cell. And the cell consists of all points P in the plane for which fa of p is less or equal to fs of p for all sites s. So for s equals b, s equals c, and so on. And the cell of A looks like this. So then what's the Voronoi diagram? It's the subdivision of the plane into all the cells for all sites. So cell of A, cell of B, and so on. Now the Voronoi diagram is also a plane geometric graph, which has vertices, which is where 3 or more cells meet each other. And it has edges, which are line segments where 2 cells meet. In fact, Voronoi edges, such as this one here between A and B, consist of points in the plane that have the same distance to, in this case, A and B, and such that no other side is closer. And so this is the Voronoi diagram.
Of course, it's named after Voronoi, in fact, Georgy Voronoi, in 1908, he described the diagram.
Right, but as is common with many of these natural geometric concepts, it's been discovered and rediscovered many times. So, like in the 17th century, Reine Descartes mentioned it.
Right, yeah. And then I think in the 1850s, it was again discovered twice independently.
Right, exactly, yeah. So in 1850 by Johann Peter Gustav Lejeune Dirichlet.
And 54 by John Snow. And also noteworthy is that in 1911, so only 3 years after Voronoi, the diagram was again rediscovered by Alfred Thiessen.
That was in meteorology, yes. And in fact, in meteorology, the Voronoi cells are called the Thiessen polygons.
So it's actually not so clear how to find any algorithm for computing the Voronoi diagram, even if we just want to find a trivial brute force algorithm.
Right, it's even though we can try out like all pairs to see if part of their bisect, if they will define part of the Voronoi diagram, it's still not clear how to kind of stitch those together, or we still need some geometric insights to figure out which parts of those will actually be in the diagram.
Right. Yes, actually the first algorithm to compute the Voronoi diagram was only published in 1986. So that's Stephen Fortune.
Right, exactly, yeah, that's the wavefront algorithm. Or the beachline algorithm.
Right. Yeah. So how does this algorithm work? Well, the idea of Fortune's sweep line algorithm is to sweep a line or some elongated object down across the plane. So as we're sweeping down our line, at some point we'll sweep over a site of a snowball vendor. And when that happens, we insert it into the diagram. And for every site we've already encountered, we're going to maintain a parabola. And the idea is that this parabola is exactly the set of all the points in the plane which have the same distance to this site as to my line. So now, as my line is sweeping down the diagram, these parabola are also going to move down, and they will get bigger and wider as we go along. And we keep doing this until at some point we meet another site. And at this point, a second parabola appears. So these moving parabola are also called waves, and that's why this algorithm is also called the wavefront algorithm. Just like waves approaching the beach. those waves which are closest to the line form the wave front. So we keep doing this, moving our line down, the parabola keep growing until at some point these parabola will meet each other. And now the trick is that the points where these waves meet each other are going to trace out the edges of the Voronoi diagram. So why is that the case? Well, the wave of one of our sides, A, is defined as the set of all points which are as close to A as they are to this line. So the distance from any point on this wave to A is the same as the distance of that point to this line. And similarly, for a side B, the wave of B is defined as the set of all points whose distance to B is the same as the distance to that line. So now if I look at the points where these waves meet each other, well, that point is on the wave of A and on the wave of B. So that means that for this point, the distance to A is the same as the distance to the line. But the distance to B is also the same as the distance to the line. And therefore, the distance to A is the same as the distance to B. So this point is on the Voronoi edge between A and B.
You see those waves touching? If you look closely, you see they're moving along a Voronoi edge.
So now as we keep sweeping our line, eventually we will sweep over another side. And as the line sweeps over all of our sides, eventually these points where the waves meet will trace out the entire Voronoi diagram for us. So the actual algorithm is quite a bit more complicated than this, because computers work in discrete steps and we cannot just continuously sweep a line and keep track of what happens. But the details of that algorithm go a little bit too far for this video, but we still hope you got the idea. And if we analyze all of the bits and pieces, then it turns out that in the end we can implement this to run in n log n time. So that's an amount of time in the order of n times the logarithm of n.
So let's get back to our original question. Given a set of sites, how do I know which one is closest to me? Instead of storing the sites in a list, we can compute the Voronoi diagram and store that. Then in order to find the closest site to me, I just need to find the Voronoi cell I am in. But how do I know which cell I am in? Well, for that we need another idea, a point location data structure. A data structure is a way to store data such that we can quickly answer certain questions or queries. So in our case, the data are the regions in the plane, or in this case, the Voronoi cells, and a query is the location I'm in. The data structure should then tell us which of the regions or Voronoi cells contains the given query point. Point location is another topic that goes beyond the scope of this video, but generally the idea is that it's fine to take some time to construct the data structure as long as a query is fast. So it takes less time to do a query. For point location, one can build a data structure in n log n time such that a single query only takes log n time. And if you're interested to learn more, we have another video on point location. There are several other algorithms to compute the Voronoi diagram, but they're all very different in nature. But they all have the same runtime, well, the same order of magnitude of runtime.
Right, and actually there's no algorithm which is faster. There's one thing we have to tell you.
Right, I mean, this wouldn't be a video on Voronoi diagrams without us telling you about that.
It's a very important fact, a central fact in computational geometry.
Exactly, yeah, it's very important. It's the Delaunay triangulation. So the Voronoi diagram and the Delaunay triangulation are dual graphs. And in fact, we have a whole other video on the Delaunay triangulation where we also talk about the algorithm for computing the Delaunay triangulation.
So importantly, because the Delaunay triangulation and the Voronoi diagram are each other's dual, we can use algorithms for one to compute the other. Alright, so the Voronoi diagram and the Delaunay triangulation are each other's dual graph. So what does that mean exactly? Well, if I have a set of sides S, then the Delaunay triangulation is a plane geometric graph. So our sides are also known as the vertices of the graph, and the graph also has edges which connect the sides and faces. And in the case of a Delaunay triangulation, all the faces are triangles. Now, on the other hand, if I draw the Voronoi diagram of S, I get another plane geometric graph. So in this case, every side that I started with corresponds to one face of the Voronoi diagram. And the Voronoi diagram also has edges and some vertices. And here the vertices are always places where three of the edges meet. Now my claim is that every vertex of the Voronoi diagram corresponds one-to-one with one of the faces of the Delaunay triangulation. So here, this vertex corresponds to this highlighted triangle here. In general, the vertex doesn't have to be inside the face it corresponds to. For example, this Voronoi vertex corresponds to this triangle up here. But generally there is a one-to-one correspondence, and even more, every edge of the Delaunay triangulation also corresponds one-to-one to one edge of the Voronoi diagram. Now, I'm not going to prove this claim here, but if you did watch both this video and our video on Delaunay triangulations, then I challenge you to try and prove this yourself.
Enough of that. I really need a snowball right now.
Luckily, I've computed the Voronoi diagram of all snowball vendors in town, so I'm safe.
Congratulations! You made it to the end of another video in our series of computational geometry concept videos. We hope you enjoyed this one and learned something about
Voronoi diagrams. Yes, so this time we learned about Voronoi diagrams and how they can be used to find the closest site in a set of sites.
And if you want to know more, as always, we've put links to all of our sources in the description, as well as to some of our other videos, such as the one on the Delaunay triangulation or one on point location.
Yep. Thanks for watching.